Okay, so, oh man, section before the last section. Talking about section 15.5. You today are going to learn what Green's theorem is, what it entails, and how it makes life beautiful, or at least easier, making your line integrals much more easier for specific cases. So let's think of something. So far, what we talked about, we had this idea of a line integral through a vector field. We said, well, we can find the work done by moving a particle along this curve through a vector field by just, if we have the curve itself, by just doing a simple dot product. We did that before. And then we said, well, what happens if we have a conservative vector field? And we had line integrals over conservative vector fields, talked about independence of path. That was the last section. We spent a lot of time doing that. Now it's a different idea. What happens now if we get a little bit more specific about the curve? What if the curve is not just a couple segments going along, or not just this random curve going through the vector field? What if this line integral, notice the line integral over a curve, has this curve that encloses a region that just starts at one spot, goes through a vector field, and ends at that same spot. Furthermore, that curve is a simple closed curve. What's that? A simple closed curve. What's that mean? Simple means it doesn't cross itself within the region. Okay, so it doesn't do like. Doesn't do that. It starts someplace, does whatever it wants, but it doesn't cross itself. That would be a simple closed curve. This would not be a closed curve. Do you see the difference? Your starting spot and your ending spot have to be the same, and you're not crossing yourself. That means that you're a simple closed curve. I don't know if you're okay with that one. Furthermore, let's assume that this curve is traveled in the positive counterclockwise direction. So we start someplace and go counterclockwise, and that's what that means, counterclockwise direction. So, what are we dealing with? Are we dealing with vector fields still?
Yes.
Well, we're going to find out. Are we dealing with work? We're going to find out. Are we dealing with line integrals? Certainly yes. But line integrals where we have a specific type of curve. What type of curve are we dealing with in this section with Green's theorem? What's Green's theorem going to have to do with? Curves that do what? Oh goodness, this was supposed to be like, you got it. Do you understand what C does? What's C do? On a plane. It closes a region on a plane. This is going to come into play here. It closes a region in a plane, doesn't cross itself, doesn't close two regions like this does. It encloses one region on a plane, starts and stops at the same spot, and is traveling in the positive counterclockwise direction. So you understand the premise for Green's theorem. Now, do you understand Green's theorem yet? No, but I'm about to show you. So here's what Green's theorem is. Invented by the Incredible Hulk, I'm pretty sure. So that was a joke. It's not the Incredible Hulk. Or Bruce Banner. He's pretty smart. So Green's theorem says, well, what happens? What happens if our line integral has a simple closed curve? Then really this C is very specific, and we draw a circle right there, saying that that's a line integral where the C is a specific type of curve, a simple closed curve that's containing this region. Is traveled around the region in a positive counterclockwise direction. So, here's what Green's theorem says. Green's theorem says that this line integral over a simple closed curve. By the way, do you remember that format, having this p dx plus q dy? We're about to see where that came from. Equals this. It's going to look a little strange to you until you wrap your head around it. That, ladies and gentlemen, is Green's theorem. What it states this. It states that a line integral for a simple closed curve is equal to, well, let's look at it. Let's look at it. Check out the notation. Firstly, can you recognize line integral here? Simple closed curve. That's what this says. See a little arrow going positive counterclockwise direction. Well, let's look at what Green's theorem says. I'm not going to prove Green's theorem. It's kind of beyond our time limit, firstly, and the necessity to do in this class. But let's look at what this is. The Green's theorem says a line integral over a simple closed curve is equal to, oh my gosh, what is this? That's a double integral over a region. It says that the line integral for a simple closed curve equals the double integral over the region that curve contains. That's what that says. Now, why is that important? Because double integrals are really easy, and they're really nice to deal with. And line integrals can be a real pain. When they were conservative, they were kind of nice. When they were non-conservative, they were a real pain. We had to have a vector function for each different curve and then add up the different integrals and reparameterize it. And if we didn't have a curve, then we were in serious hurt. Does that make sense? That was a problem. We're going to deal with some of those issues right now. So Green's theorem, blah, 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 a line integral for a simple closed curve is equal to a double integral over the region that the curve contains. Now, let's use some critical thinking here. Think about this. Why does the curve have to be closed? Why does the curve have to be closed for Green's theorem to work, keeping in mind that's a double integral? Why? If I don't have a closed curve, do I have a region? If I start crossing this, how many regions do I have? That's a problem. So, with Green's theorem, you get a simple closed curve because if you don't have a closed curve, you don't have a region. If you don't have a region, a double integral doesn't make any sense at all. You have to have this. This is all Green's theorem says. It says, hey, if you got a line integral over a simple closed curve equals a double integral over the region that simple closed curve contains. That's it. That's literally all it says. Show of hands if you're okay with that. Now, what is all this junk? And where is it coming from? This is Green's theorem, and I'm not gonna prove that, but I'm gonna show you where this stuff comes from because we've seen it before. And I said this. I said just kind of think about this as ds being split up by the nature of that derivative. But I only said that because we hadn't talked about this yet. I'm gonna show you where it comes from. So let's find out where this comes from. Let's let a vector field be defined. And furthermore, if we have a vector field like that, let's define a curve. Remember doing that? Just now? Remember having vector fields? Moving back to a while back, vector fields, and we had these curves through the vector field, and that was like 2 sections ago. Then we said, what about conservative? Oh, we don't need a curve. But before that, we had to have a vector field, we had to have a curve. I had to that you understand that. We had to have both. That's our vector field, that's our curve. And then we said, well, wait a second. We did a lot of stuff with dr, and dr was, happened to be the partial derivative of this with respect to x, and the partial derivative of this with respect to y. That's where we got that from. I'm just using a different notation for the partial derivatives, but that's where we got that from. And so, well, wait a second. What would happen if I took f dot dr? But if I did that, well, if I take f dot dr, then that's p I plus qj. That's our vector field, dotted with this thing that I just got, the dr. Hey, firstly, is a dot product going to work here? Explain why or why not. Is a dot product going to work?
Yes.
Why? Both vectors. If I do the dot product, then we end up getting, well, you can see it. Component, no i's, no j's. Component, no i's, no j's. Here's what we just got out of this. We got that f dot dr equals this right there. You guys okay on where that came from? Now, let's integrate both sides. Let's talk about that. Furthermore, let's integrate across a simple closed curve. But wait a second. Wait a second. Wasn't this? Hey, do you remember what that was? Do you remember what that represented? Do you remember what we did when we had a vector field dot dr over a curve? What did it mean? This was work. But wait. If this is work, look at this. Is this also work? Is this also work?
Yes.
Yes. It's just a specific type of work. What this means, every single time you see it, this right here, this is work. This is the same exact thing that we had for work. It's just our curve is specific. Our curve here is a simple closed curve that bounds a region. That's what that means. Well, if that's work, and I have them equal, then this is also work. This is work done. This is work done over a simple closed curve through a vector field. That's what that means. Does that make sense? So every time you see that, that's what that means. So this is work done along C, some curve C, some simple closed curve C. Through a vector field. By the way, and this is where I can make the statement, this is where all that stuff, if you think back to two sections, we had ds, and then all of a sudden I changed it. I said, oh, now we have dx and dy. And I said, just kind of think about it as your ds is in two spots, and you're kind of breaking up that derivative, sort of. The dt is kind of broke up. I did it so you wrap your head around it. What it's really coming from is this idea. So every time we saw that 2 sections ago when we first started talking about line integrals, and then we put them through vector fields, we hadn't talked about putting them through vector fields before we got some of this. This is where that came from. So every time we did the line integral from before, and we had the p dx plus q dy, do you guys remember that stuff from a while back? We've already seen it. That represented work done. That represented a vector field already. It's just I couldn't explain it because we hadn't talked about work done through vector fields. You guys see what I'm talking about now? Are you alive still? I need your focus, I really do. Green Theorem doesn't have to be that hard, but you have to focus on it. So let's go through maybe a 45-second recap here to make sure we get the idea. The idea is we have had line integrals for a long time now. What if we have a specific type of curve? What if the line now for our line integral is a curve that creates a simple closed curve that bounds a region? So this region's in there, and we're traveling it in a positive counterclockwise direction. Then we have now a different look for it, but it's coming from the same place. Where this comes from, it's just coming from, hey, a curve through a vector field that happens to be a simple closed curve. It's done, here's the dot product, it's exactly the same thing. It's coming straight from that. You guys see that all this is work done through a vector field. Show of hands if you do. Along the simple closed curve. That's what that means. So this is work done along a simple closed curve through a vector field. That's what we're doing every single time that we have that. But wait. Wait a minute. Wait. You tell me we're starting at a spot, right? We're going through a vector field. And we're doing work. And we're coming back to the same spot. Isn't the work just zero? Isn't the work just, didn't we find that last time? We did the exact same thing. Oh yeah, the work is zero. Because if you do work along a simple closed curve, then if you're moving a particle from one spot back to the same spot, aren't you doing no work? Because I literally showed that in the very last section. But no, I said something there. I showed that in the very last section. Is the work done on a simple closed curve? If I go here and go back, is that always going to be zero? What did the last section have to do with conservative vector? That's the whole key. You listen carefully right now, okay? The last section said, yes, the work done here is zero for a simple closed curve. If you have what type of vector field? If you have what type? Conservative. That makes sense. If it's conservative, you're coming back to the same spot, you've done no work. So here's the thought now. If this is dealing with simple closed curves over vector fields, which I've just proven that it is, what's the type of vector field that we have for Green's theorem to take place? Is it conservative? No. If it was, they'd all be zero. So I'm going to go through it again because some of you didn't get it. Simple closed curves on conservative vector fields would give you work of zero every time. This was for conservative vector fields. Only. That was for conservative vector fields. So let's put it this way. If these are all conservative vector fields, how much would all of these line integrals over a simple closed curve be? They'd all be zero. So does Green's theorem generally deal with conservative vector fields? No. That's where Green's theorem comes into play. So I'm going to say it one more time, get your head wrapped around it. If you have conservative vector fields, the line integral through a conservative vector field of a simple closed curve is zero. If you have non-conservative vector fields, Green's theorem shows us what to do. In fact, I was going to wait till later, but I can't handle it. The suspense is killing me. Do you remember how to show that vector fields are conservative? Do you remember how to show that this right here that right there is how you show that vector fields are conservative? Do you remember that? Subtract this side. Subtract this from both sides. What is it?
Zero.
I will prove it to you right here that Green's theorem does not deal with conservative vector fields. You ready? You ready? You ready? I hope you're looking. If you blink, you're going to miss it. You understand this concept, right? This proved conservative vector fields. If we have a conservative vector field, this would be zero every single time. In fact, we use that in Green's theorem. We say, hey, if you ever get a zero in here, your work done zero. Because it just proved that your vector field's conservative. And if you just proved your vector field's conservative, for a line integral over a simple closed curve through conservative vector field, you got a work done of value zero. Isn't that kind of cool, right? Is it starting to make sense to you? So we get these line integrals that were just random pieces. We did that 2 sections ago. Then we said, let's assume that we have line integrals, but it's over conservative vector fields. Now we did that. Now let's assume that we have these curves that connect, but they don't have to be conservative. That's where we're at right now. Question.
So can we use this to prove a vector is conservative if we want to use the conservative vector functions?
A vector field's conservative?
Yes.
Be a lot easier just to do that,
Okay.
right? You kind of do it intrinsically in Green's theorem. Do you guys see it? Do you guys see that this is conservative vector field? Do you see if you subtract both sides you get 0? Do you see that this piece, it's in there? That's what I'm saying. Dude, Green's theorem is going to show up whether you have a conservative vector field or not. If you get 0, conservative, done. Just put 0. You're done for Green's theorem. If it's a simple closed curve. You guys get it? If you get something in there, you have a double integral over a region that's really easy to define. And like half your variables are generally gone because you're doing partial derivatives. It's freaking awesome. Okay, it makes your life easy. Green's theorem's awesome. It's cool. It's a cool thing. So here's our walkthrough one more time. Our walkthrough says that simple closed curve for line integrals over conservative vector fields gives you work done of 0. Over non-conservative vector fields, Green's theorem. So I'm going to write one statement out. You need to write it down. So Green's theorem deals with line integrals of simple closed curves through non-conservative vector fields. Because if they were conservative, we would get 0 every time. Write that statement down, would you? Green's theorem deals with line integrals of simple closed curves through non-conservative vector fields. Let's say screw it up. Let's say that you go, oh my gosh, I did Green's theorem on a conservative vector field. Is it a big deal? Not really. You're just going to get 0. Because this is the proof, right, for conservative vector fields. So if you just go through Green's theorem, you're just going to get 0. So it's not even that big of a deal. All I'm saying is that Green's theorem is relevant for non-conservative. It's not really relevant for conservative because we'd get 0 anyway. Does that make sense? That's it. That's the whole theorem part of this stuff. Honestly, right now, all we have to do is practice. So the thing that we're going to practice is how we change from here to here. There's only 2 things that we need. Actually, only really one thing. You need a non-conservative vector field, which is going to show up no matter what. And you need a simple closed curve. That's the biggest idea. So we got to show that we have a simple closed curve. You guys understand the idea? If you don't have a simple closed curve, you don't have a region. If you don't have a region, you can't do a double integral. So that's the whole premise for Green's theorem. The whole conservative vector field thing is going to show up when you calculate that. So I'm going to show you how to do it. We're going to set up a ton of them. We're only going to work through a few of them. Again, this is all about the setup. You guys can do some basic integrals here. Let's start with this one. So let's take a look at the line integral. What's that say right there? What's the line integral telling you? It's going to have a simple closed curve. And then it's going to give us that curve. Here's what I want you to do. I want you to do a few things about this. Number one, I want you to draw that simple closed curve every single time. Every time. Why? Because that curve has to contain a region. And how we set up our double integrals is draw the region every single time. So can you please take some time to draw that triangle?
Special water all over that.
So I'm telling you it's a triangle, so I'm telling you triangles are simple closed curves. We're starting, it doesn't really matter, we're going positive counterclockwise direction, that's a simple closed curve. Can you guys see the region that it contains? If it wasn't simple closed curve, we wouldn't have a region. That brings me to one point here real quick. Please listen carefully. Let's say that I didn't tell you it was a triangle. Let's say that it was just these two segments right there. If I don't contain a region, I can't use this. I fall back to two sections. I'd have to redefine segment. Remember doing segments? Remember doing that? Vector function of segments? One of them, two of them, two different integrals, and you'd have to do it. Redefine all that stuff in terms of t. And then dx in terms of t. This, remember doing that stuff where you plugged in t's for here, you took a derivative, plugged in the dx equals something dt, t's, dy equals something dt, and you did that integral? You'd have to do that for two of them. So, is Green's theorem going to make your life easier? You better believe it, yes, if we have a simple closed curve. So if you understand that concept, that's a big deal. But we've already done it, just so it would suck. Also, one thing I want you to do here, the second thing, sometimes, and I hate it when they do it, but they do it a lot, books will have these switched up. I will always write it dx dy for you, but some do dy dx, blah, 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 they switch it around. Would you please be very careful and right now put a p above the part right before dx and a q right above the part for dy. That's what this is saying here. The p is associated with dx. The q is associated with the dy. So put that up there somewhere so you don't get lost. Is that a good idea? Yeah, it's a good idea. So this right here says, which one's this one? And that's the Q, just so you don't get lost on this stuff. Head nod if you're okay with that one. By the way, if you wanted to, you could find the vector function that's creating this right now. If that's P, look, if that's P and that's Q, the vector function is just Pi plus Qj. If you wanted to, I'm not saying you need to, but your vector function right here is x cubed I plus x y j. It's coming from something. It's coming from the vector, I think I said function, but it's coming from the vector field. That's what that is. That's the part of it. Head nod if you're okay with that one. That means that you could show whether this is conservative or not. You don't even have to write it, but this is where it's coming from. It's why this part is relevant to being conservative or non-conservative. So let's go ahead and let's see if Green's theorem applies. Firstly, is this a line integral over a simple closed curve? Then Green's theorem applies. Can you define the region that curve encloses? Then we can create a double integral. So here's how it works. It's honestly not hard. What Green's theorem says is that for this particular simple closed curve, all I need to do is create a double integral over some region. I'm going to take the partial derivative of the q component with respect to x. Can you tell me what that is, please? Partial derivative of q with respect to x. This is why we write it. This with respect to x. Remember that? It's kind of like the backwards thing that we did for checking conservative. This with respect to x minus this with respect to y. What's that one?
0.
Do yourself a favor. Do yourself a favor. Do me a favor, because I gotta grade your stuff, okay? Don't ever skip this step. Ever. Always write out this to your double integral without worrying about your region yet. Always write that out. Can you guys agree to do that for me? Always write that out. Always write out this integral just like that. Now, what's it say? Man, it says something really nice. What it says is that this line integral over simple closed curve is equal to the double integral over the region that it contains. Hey, now, if I stepped back an entire chapter and gave you this problem with that picture, could you do the double integral?
Yes.
That's what Green's theorem does. It takes us back to a chapter. So it goes, hey, sweet. That's why we don't skip the step. It says this is literally just a double integral. Can you define it? Yeah, I'm gonna move quickly here because we should be really, really good at double integrals. The first one is, if I'm going from 0, 0 to 1, 1, my line is y equals x or x equals y. Does that make sense? We'd say, well, then this is a double integral. You know about double integrals because I taught you. We have y in here. You go d, what? Well, I don't do the dA yet. I do it's either x or y, but I got to deal with this first. Which way would I want to go? Y first or x first? Y first is between two functions that are not 0. I would go x first, for sure. This is x equals 0. This is y equals 0. This is y equals 1. I would go from x equals 0 to x equals y. I'd ignore this one. I want x, and that means I'm going to do dx. Is this ringing a bell for you? I don't have time to reteach double integrals. Are you guys okay with that one? Then our y's would go from where to where? Yep, the rectangular numbers there, 0 to 1. That's it. dy. So R, that region, R is now just the inside of that thing, that space that you're containing. Can you do this integral? Go for it. See if you can do it. This is like the one that we're going to do. I had something on my mind, I forgot it. Don't remember. Oh, I had it. Is F conservative?
No.
Is F a conservative vector field?
No.
Why not?
It would be 0.
This would be 0. And then you'd be done. You say, hey, 0, conservative vector field, simple plus curve, done. Does that make sense? It's kind of cool. Let's see. Zero to 1, let's see here. We'd have x, y, and we're plugging that in for x equals 0 and x equals y, and then we got that dy hanging on. So integral from y equals 0 to 1, and we have y squared dy. Looks like 1/3 y cubed from 0 to 1, 1/3. We haven't had one that nice in a long time. Did you get 1/3? Now, what does it mean? That's work done through this vector field right there. Through that vector field that you could find, right? Just from your line integral. Through that vector field on a simple closed curve. This particular simple closed curve. So moving a particle around that curve one loop, if you will, in the counterclockwise direction. That's what's happening here. Are you okay with it? What happens if we reverse directions? Be negative, just the sign would change. That's what happened if we reverse directions. Also, one more thing. If this equals 0, it does not necessarily mean that you have a conservative vector field. That would show up right here. So if this thing ain't 0, you don't have a conservative vector field. Is this all making sense to you? Are you guys okay with this one? By the way, could you have done this a different way? Could you have reparameterized these 3 segments, done 3 different integrals by reparameterizing this 3 different times, and added them all up and got 1/3? Yes. Would it have sucked? Oh my gosh, yes. Do you have any idea how much headache I am saving you, or how much headache Green is saving you here? It's a big deal. It's a cool theorem. Is it hard to do? I don't know. Was that hard? Not really so much. Tell you what. Let's do one more example, and then we're going to take our break. By the way, if you're asking, why in the world didn't we do this before? Why didn't we do this before? This is so nice. Why not? Why didn't we do it before?
We weren't on the section yet.
Good. We weren't on the section. Very good. Why really didn't we do it before?
It only works for simple closed.
It does. It only works for simple closed curves. And 2 sections ago, we didn't have those. We just had segments. or we had things that were not connected. It wasn't a connected region. And then in the next section, we had conservative vector fields. So this is dealing with things that are connected, but non-conservative vector fields. That's why we didn't do it. How about the last one, and then take a break. This is going to take about 30 seconds. I want you to find the line integral for that vector through that vector field over any simple closed curve. Can you identify what P is? Can you identify what Q is? This problem is here for one reason, to make sure you actually got something about what I was just talking about. Is Green's theorem going to apply? If I tell you it's a simple closed curve, is it going to apply? So this would equal a double integral over region. Don't ever skip the step. Do not go directly to identifying the region, because sometimes you can save yourself a lot of time by just identifying this and then working on your region. I would find the partial derivative of Q with respect to, I would find the partial derivative of P with respect to, tell me something right now about that vector field. Tell me something about a line integral that's a simple closed, so a line integral for a simple closed curve over a conservative vector field.
You don't work this time?
Oh, 0. Pretty easy. So when that happens, 0. I'll take a break and come back in a bit. So for right now, we have a whole lot of practice on how to use Green's theorem. Again, Green's theorem says, hey, simple closed curve. You all right? Good, so I'm going to give a heart attack. Jeez, warn me, all right? Freaking goodness. I've had too much caffeine and my heart is thumping.
It's good.
No, it's not good. Back to normal. I got to breathe. So, what was I even talking about? Green's theorem, right. Happens over simple closed curves. Does it matter if they're conservative or not? Not really. It only is really relevant for conservative, but don't even worry about it. All I really want you to worry about is that the curve encloses a region that you can define. So your number one step right now is you look at that curve and you draw the region every time. Why? Why would you draw the region every time? Because I told you so. Why would you draw the region every time?
So we can set up our band.
So you can set up your double integral and to make sure it's a simple closed curve. Does that make sense? So draw it. So when we draw this, and listen, I'm not going to spend a whole lot of time doing it because we've killed double integrals. Like, we've beat them to death. So we're going to go really fast on this stuff. But of course, if you have questions, you let me know. So this says that I have this pathway that's bounding these two curves. There's y equals x. Here's y equals x squared. If you were to do the intersection, these things intersect at 0, 0, and 1, 1. We're just focused on one loop. Again, simple closed curve. Hey, it's got to be simple, right? It can't cross, which means it can't go down here, otherwise it wouldn't be simple. We'd have just this one, and we're going around the loop like that. Can you guys picture the loop that we just created? Head nod if you can. Okay. Is it a simple closed curve?
Yes.
Does Green's theorem apply? Let's set up Green's theorem. What Green's theorem says is that the work done of this line integral of simple closed curve is equal to the double integral over the region that it contains, this region. Don't skip this step. Write this every time. Even if you know what the region looks like, you write it every time. Because I want you to deal with the pieces in here before you start setting up the double integral, okay? I want a two-part setup. What's your P here, by the way? Did I mention to you? I don't know if I did. Did I mention to you that sometimes they flip-flop these things? Label P and Q every time. That way you don't accidentally waste a whole lot of work. So the partial derivative of q with respect to what? Gives me?
2y.
Yes. Minus the partial derivative of p with respect to...
Y.
It's easy to get confused. It's the y with the x, it's the x with the y. So partial derivative of this with respect to x is 2y. Partial derivative of p with respect to y is... That's it. Also, if you haven't noticed this yet, there's no reparameterization at all. Green's theorem takes care of all of that. You don't need a t, you don't even need a vector function. It's done for you. It's so nice. And this is dA. Don't ever skip this step. This is number one, and then you use the region that you just drew to fill out the rest of it. Let's try that right now. So I'm going to keep the inside of this. I'm going to leave this alone. I'm going to look back at my region. What would you do? Would you go along the y direction or the x direction? What do you think? I'd go y simple first because they're already solved for y. Does it really matter? No. But if I had to solve them for x, I don't really want to do that. So I'd go here first. The region, this is why we draw it. It always shows us what's on top, what's on bottom, and where to go. It's really nice. So our y simple says I need y equals, and y equals, x equals, and x equals. And I'll be going d what? dy, dx.
dy.
What's the smaller function? And the larger one? Perfect. It matches up. We're going from y equals x squared to y equals x. That's the region that's enclosed by our simple closed curve. And then I'm going from x equals what to what, please?
0 to 1.
Across this way from the constants. 0 to 1. Show if your hands feel all right with that one. Yes, no, yes? We're going to leave a lot of them just set up. Would you know what to do after this? Integral with respect to y first. So you get this y squared minus x squared y. You plug in for y, distribute, do dx, plug in for 0, 1, and hopefully get 112. Work done. Work done. By the way, if I asked you to do an interpretation, I would ask you for something like this. Tell me what you did. You'd found what's that give you? Work done along this simple closed curve through what? What vector field? That's the point. What vector field? Could you find the vector field from this?
Yeah.
So this is the work done along this simple closed curve through the vector field, which is just Pi Qj. And that's what we're doing. That's what Green's theorem does, and that is what we are doing. Ladies and gentlemen, is it making sense to you? We're going to kind of crush probably 3-4 examples here real quick, deal with something kind of really interesting. We're going to prove the formula for area of an ellipse, which you probably haven't seen before. So we'll deal with that, and then we'll probably have to call it a day after that. But we want to get through as many as we can. So firstly, what's the first thing you do every single time you're given a line integral and I tell you that? What are you going to be doing? Draw the curve. This one says that y equals 0, that's the x-axis, that's fantastic. This is a parabola that has a y-intercept of 4, opening downward. Do you know, or could you find where that intersects the x-axis?
Yes.
Where's it intersect the x-axis? Good, because if you set these equal to each other, we find the intersection. This is -2 and +2 on the x-axis. I don't know if you're okay with that one. Hey, does that region enclose is it enclosed by a simple closed curve? Yeah, that's fantastic. Show it's a simple closed curve, it's going right around there, and we have a region right inside of it. I want you right now to try to set up Green's theorem. Since this is a line integral over a simple closed curve, we've drawn the curve. We already have the region, it's fantastic. Just do Green's theorem, let's set that up. So our work is going to be equal to a double integral. What do I put right here for right now? Just right now. Just put R. Leave it for a second. Leave it until you've determined it's non-conservative. You might want to label P and Q before you begin. Can you tell me what the first part? Tell me where I get the first part, and then tell me what it is. What should I get? 1. Why? How do I get it?
Partial Q with respect to X.
X. That's great. That means it doesn't even matter. I love that. It's just 1. Partial derivative of Q with respect to X is 1. And then do I add or do I subtract? Okay, let's make sure we get that right. Partial derivative of P with respect to Y, which gives me
2.
in parentheses. What's the next thing I should have? dA. Okay, so let's practice something. Now that we've, by the way, can you write down, don't do it, but could you write down what the vector field we're working with is?
Yes.
This I plus this J, with me? So we could do that. We're finding the work done along that curve through that vector field. That's exactly what this does for us. It's given to us by a double integral. Write this down every time before you start working with your region. We've just determined that the reason why we do it is because if we get 0 here, we're done. All right, that's conservative. Is this a conservative vector field? No. Otherwise, we would have got 0. Good. Go ahead and set the region up for me. Now we're just back to double integral land. Would you go in the X direction or the Y direction? What would you do? Absolutely the Y direction first. Since this is all one function, we go from Y equals 0, sorry, grab 0. We go from Y equals 0 to Y equals 4 minus X squared. Look, if we went the other way, it would be possible, but you'd have to break that up. And I don't want to do that. I don't want to break that up into 2 functions. Does that make sense? Make it as easy as possible. Don't start switching functions. That would be D. Means they got to have X between, that's what we solve for them, -2 and 2. Head nod if you're okay with that one. Would you know how to solve that double integral? Integrate with respect to Y first? Man, honestly, compared to that, that's really easy. If we had to reparameterize this curve and that segment, that gets nasty. And then we'd have to integrate 2 times after switching all the variables to t and then add them up. Green's theorem just saved us a tremendous amount of work. A lot. That's nice. The answer here, if you want to check it yourself, is -352 over 15. 2 things. What is it? Work done over this curve. Well, along. Let's say along this pathway, the positive clockwise direction, through this vector field. That's what we're doing. What if we reverse directions? Positive work. Yep. Change the signs. That's all I got to get you to know. Let's do maybe 2 more kind of easy ones, and we'll talk about an interesting idea. Then if we get back to it, we'll do a couple others. Okay, we got a line integral. I'm telling you it's a simple closed curve, which means that you have to have a connected region there. It's got to be bounded by those 2 things. What's the first thing you do every single time when you have a simple closed curve over a line, for a line integral? Let's draw that. Hey, what's Let's start with this one. It might be a little easier. What's that?
Circle,
Radius, center?
origin.
Wow, that's the worst circle that I've had in a long time. Goodness. That's that circle. Now, I'm drawing a dotted line. Why? Well, what's that? This little segment. This segment that goes from negative 1, 0 to 1, 0. So we're going to make a choice here. We're going to pick the upper half circle versus the lower half circle, but we don't have two regions. We have only one region that's bounded, either the top or the bottom. We're going to choose the top one. Head nod if you're okay with that one. Do you guys see the simple closed curve? Do you see why we draw these things all the time? If we draw them all the time, we get a really nice picture of what's going on. This right here is our simple closed curve that contains a region. Is Green's theorem going to apply?
Yes.
Let's go ahead and set up Green's theorem, please. Well, I know that's P, I know that's Q, that's kind of nice. What's the first thing I should put? I'm going to talk about why in this example. It's why we do it. One of the reasons why we do it. We set this up first. What goes right there?
R.
Don't write anything but that until you take a look at your region, okay? So we have this. We have the partial of this with respect to
X.
minus partial of this with respect to,
Y.
and then we have a dA. A dA, not a d anything else. Not a dx, not a dy, a dA. Don't, I said it 4 times, don't ever skip this step. Why? Here's the one of the coolest things about Green's theorem is it changes curves into looking at regions. When we did line integrals before, we did a right half circle. Do you remember that? And we couldn't use polar because we didn't have a region. Do we have a region? Green's theorem lets us change from curve to region that curve contains. If that's the case, we're now back to basic double integrals. So the reason why we write this is because it switches your head. It says line integrals, no. Double integrals, yes. What's my double integral look like? That. What's that look like? Polar. Make sense? We now get to use stuff like that. That's brilliant. Fantastic. So for polar, well, I know that x squared plus y squared equals r squared. I know that r equals 1. R squared equals 1, r equals 1. That was pretty easy. Make sense? I know that if I'm going to set this up, I have a double integral of something on the inside. We're going to do it the same way every single time. I need to go, oh, hey, for polar, oh my gosh, ringing a bell. Polar, what do I have to have when I do a dA into something else, into the polar? Hey, you remember it. That's why we write the dA. So it rings a bell, and you go, dA, change it to RD, RD theta. We're now just working with double integrals. We're double integral land. Here, we have to go R first. R goes from 0 to R equals 1. Theta, oh, theta. Firstly, are you guys okay on the R portion of it from 0 to 1? Talk about my theta. Where's it going from?
0 to Y.
Good, it's not a full circle. So fancy people are with that one. Sweet, let's keep on going. What goes here? Let's narrow it down. Not x's. Okay. R cosine theta, therefore this would be negative r squared cosine squared theta. Negative that. Are you buying into this stuff? You all right with that one? Yes, 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 yes. Okay. Could you work it out? What's the first thing you'd do? Combine the r's, get r cubed, you get a negative 1/4 r to the 4th cosine theta. Plug in for 0 and 1, get a 1/4 out of that, and then you get this cosine squared that you'd have to deal with. Okay, so that's those even powers of cosine. Probably use 1/2 1 plus cosine 2 theta. Evaluate it. Not a huge deal. I want you to get -1 pi over 8 out of this. We're on a roll, but I gotta make sure that I'm not just killing examples here. That I'm giving you something. Are you understanding the idea? Okay, let's do. Let me have you practice one more. Go for it. I want you to do it completely by yourself. Did you draw your region? Did you set up Green's theorem? That's why we don't do this. Second reason why we don't ever worry about the region is because when you start setting up Green's theorem and you go, hey, that's my P, that's my Q, with respect to X gives me 6X, with respect to Y gives me 6X. Tell me something about this vector field. Tell me something about a line integral of a simple closed curve, and I don't even care what it is. That's a simple closed curve over a conservative vector field. What is it? Don't have to worry about it. I didn't draw it here because we don't have to worry about it. That's kind of cool, right? Sharp, put the pieces together. That's fantastic. Now let's ring a bell for a while. What's that give you? What's the double integral over R of 1 dA? It's area. Area of what? Area of what? Area of the region. So, if any line integral over a simple closed curve ever, by Green's theorem, gives us 1, double integral of 1, if that ever happens, then what this is giving us is the area of the enclosed region of that curve. Now we're going to do some razzle-dazzle, okay? We're going to invent something here. I kind of worked on this on the side just to make sure you saw where it comes from. We're going to invent something. We're going to invent a formula that gives us the area of the enclosed region every time. You see, the problem is, look at the problem. We're never given that. We're always given line integrals, right? I want to create a line integral that's going to give me area every single time. Are you guys following? So we're going to work backwards. Here's how we go. I want this to happen. Okay, well, if I want that to happen, then what my goal is I want to eventually make this double integral of that. I want that. So I need something that I'm going to split up. So what I'm going to do here is I'm going to change this. I'm going to rewrite this as 1/2 the double integral over R times 2. Because I want to split this up somehow. I want something easy to split up. And I know that 2 splits up really nicely if I'm looking at subtraction. So here's my goal. I'm trying to get this to look like this so that I can create a line integral. Does that make sense? I want that. So I want to get from here to here. So from here, okay, well, if I want subtraction, how can I split up two? There's a lot of different ways. How can I split up nicely so that I still have 2, but I have a minus in the middle? How could I do it? Any ideas? I don't want to do that because I want to. Okay, I got an idea. How about that? How about that? Let's try that. Is that still 2? Does it fit this model? Okay, so watch the magic happen. If that fits that model, then this piece has to be, or we're going to let it be, the partial derivative with respect to x. And this piece has to be the partial derivative of p with respect to y. If we undo those pieces and put them here and here, how would you undo a partial derivative with respect to x? You'd integrate with respect to x. Undo the partial derivative with respect to x. We did it already, we did it last section. Take an integral with respect to x, it would undo that. Hey, what's the integral of 1 with respect to x? It's x. That's giving me my q. Now let's try this one. Remember, this and this are equal. So we're structuring this in order to get this. That's the idea. What's the integral? Remember, this was a partial derivative of p, that guy. With respect to y, it gave me -1. So integrate with respect to y. What's it give me? Integrate. What's the integral of -1 with respect to y?
-1.
And that goes here. Let's double check that. If I take the partial derivative of this with respect to x, does it give me 1? If I take the partial derivative of this with respect to y, does it give me -1? And if I add those together, do I get 2 times 1/2 give me 1? Then this is a formula for area. This is a formula for you don't look excited. You should be it's kind of cool. You're like, oh, I don't care. You should care. This is the formula for the area of any simple closed curve, the region of any simple closed curve. That's what that gives you. So where's it coming from? Kind of some math magic, granted, because I made it up. Well, I didn't. It's been around for a long time, but we just invented it. But that's a formula for the area of the region contained by a simple closed curve. Are you guys okay with that? What that means is this. Take any simple closed curve, and even if you have to reparameterize it, you plug it in there, it's going to find the area. We're going to try that right now. We're going to try that with this. Let's say that we, let's take a look at an ellipse for a second. That's your standard ellipse. Does it look familiar to you? Yes, no? Okay. Oh, we could write that. We could do the same thing. Well, if you remember back to reparameterizing things for like circles and ellipses, anytime we have something squared plus something squared equals a number, we typically choose this to be the parameter cosine t, and this, or theta, and this to be the parameter sine t, or sine theta. So we could do that. So x over a would equal cosine t, and y over b would equal sine t. And if I solve them, then x equals a cosine t and y equals b sine t. Are you guys okay with that one? It's kind of basic reparameterization that you had in Calc 2. what could we do with it? Well, here's the deal. If I can reparameterize, look, this is a general ellipse. I'm not making any statements about these right here. This is a general ellipse. I'm not making any statements about the values. This is a reparameterization for an ellipse. I'm not making any statements about A or B. This is general. Does that make sense to you? Well, but wait. If I want to find the area of the ellipse, and true or false, an ellipse is a simple closed curve. And if I want to find the area of that ellipse, if I can reparameterize the curve right there into x's and y's, I can plug in those x's and y's, it will give me the area of that curve. So we're going to try that. Okay. Well, in order to do it, I also have to have dx. You say why we have to have dx? And I have to have dy. Okay, well, we're basically just reparameterizing this curve into something in terms of t. Everything's gonna be t. Does that ring a bell? Which means that all we need to know is what bounds of t give us that full curve. What's going to take us around the full curve of this ellipse? T equals, what gives us around the whole circle? 0 to 2 pi. So our area, I'm not going to write it twice. What we're going to be doing right now is for every x and for every y, for every dx and for every dy that we find in here, we're going to be substituting in. So we're going to be reparameterizing the whole thing. This is a formula, guys. It's going to give you the area of that that's enclosed by that curve. This is a curve. It's an ellipse. It's a simple closed curve. The 0 to 2 pi for the t that we reparameterize in takes us around the whole entire curve one time. It sweeps out the entire area. Is this okay? So let's fill the formula out. Okay, what's a simple closed curve? Well, it's the curve that we've just reparameterized from t equals 0 to t equals 2 pi. Inside, we have a negative y. We have a dx. Because we took derivatives with respect to t, we have a dt. We have a plus. We have an x. Then we have a dy. I want to make sure that you're okay with this. Do you see that this right here is this formula as reparameterized by what we do our ellipse? Show of hands if you do. You see that? Okay, so let's finish it up. Do you see all the beautiful things that are going to happen with this? Negative times negative? Both of these have dt's. And both of these have a times b. Can you make the jump algebraically with me? Yes, no. Yeah. How much is all this? 1. So we end up getting 1/2. Okay, fantastic. AB, what's AB? What are AB? With respect to t, what are those? Those are constants. Integrate this with respect to t. You can pull AB out front. You're just going to get t evaluated from t equals 0 to t equals 2 pi. Looking pretty good to me. What this equals is, well, if I multiply by 2 pi, the 2's are gone. I get AB times pi. And you go, what? That is the area of an ellipse. Have you ever seen that formula before? You might have. I don't know if you have. We just use calculus to solve that. Analytic geometry, man, that's calculus. Boom. Area of an ellipse. Now let's put it into practice. I want to do at least 2 examples on this so that you get a feel for it. If we can do 3 or 4, I'd love to. They go pretty quickly, but I think we're going to run out of time. So let's try one. Let's look at our curve. True or false, simple closed curve. Does Green's theorem apply? Let's set up Green's theorem. Can you identify P and Q and set up Green's theorem? For the sake of time, I'm just going to help you out with it here. If we set up Green's theorem, you make the R every single time. Take the partial derivative of this guy with respect to what, please?
X.
1 plus e to the x cosine y. Do you see where it comes from? Minus the partial derivative of this with respect to what? Y, which would be e to the x cosine y. dA. What does it give us? What's the argument of the integral? What are we going to have in it? Goodness. What happens? What's it mean? What's it mean? This is area. Area of what? Of the region. What's the region? Do we have a formula to find out the area of an ellipse? What's your A? What's your B?
2.
So the area of this ellipse, which is the region, you guys get it? That is the region that this simple closed curve contains. The area of the ellipse is 3 times 2 times pi, 6 pi. We just found the line integral over that ellipse by doing kind of backwards work here. We just found the area of the ellipse that contains. Isn't that kind of cool? So what's it mean? Well, that's literally the work done going around that ellipse one time through whatever that vector field is. Make sense to you? Let's go ahead, we'll do one more, and then we'll probably have to call it good. If I can do one after that, I'll try, but I don't think so. First, I want to think about our region. We don't have ellipses here. What do we have here? Let's draw these things. The union means that if we draw these are both centered at the origin. One's got a radius of 1, one's got a radius of 2. And what we're looking at is the area between those two things. Does that make sense to you? That's what we're looking at. Hey, let's see what happens here. Simple closed curve? Well, yeah, but we're looking at the union of that. So this and that and this area between them. Well, let's see about this. If we try to apply Green's theorem, we have this is P, this is Q. We get, what? Oh, no, be careful. The partial derivative of this with respect to x is 1 minus, what's the partial derivative of this with respect to y? Zero? How much is it?
2.
Oh, but wait a second. I don't have anything that says about 2. What can I do with the 2?
Take it out. Take it out.
we're dealing with some pretty cool stuff here, folks. What we have here is 2 times whatever the area of this region happens to be. That's what that line integral is going to be. That's what that says. The work done by traversing this and that's the idea. So, okay, well, if we can figure out that this is Green's theorem, make it 1. This represents this area of that region that's contained by those things. Well, how do you find the area between 2 circles? Well, okay. What's the radius of this circle? Radius of this circle? Pi r squared minus pi r squared. 3, well, almost 3 pi. This would be, do you guys see where the 2 and the 1 are coming? Well, this is 2 times 3 pi. 6 pi. I promise they don't all come out to 6 pi. Okay, just coincidence here. But that comes out to 6 pi. We can use area because it represents area. What this double integral over the region with an integrand of 1 represents is area of the region. If the line integral by Green's theorem also represents the same area, then we're solving line integrals by finding area. Does that make sense? Let's say if you didn't get it, like, oh my gosh, I don't understand any of that. Could you still set up a double integral? Well, sure. If you, from right here, if you had 2, dA, this is why I always write it, every single time. dA changes to RD theta. You're now using polar. R goes from starting 1 to 2. We're going all the way around that joint circle. If you can, I got time. If you can see it, this would end up being, let's see. Ooh, 2 minutes ahead. Actually, let's do that. Much more easy. 3. Do the same thing. A lot more work though. It's the same. It's the same concept. They represent the same thing. What I'm trying to get you to see is that they represent the same thing. Have I done that? Do you understand the concept I'm trying to get you to understand? The idea of line integrals into double integrals. That's Green's theorem. I'll finish up the rest of it next time. The last 2 examples from Green's theorem. Let's review what Green's theorem means very quickly. We're going to do our last 2 examples, and I'll introduce you to the rest of the world for Calculus 3, what this all means. So, what Green's theorem says, if you have this vector field, what type of vector field does it need to be for Green's theorem to work?
Non-conservative.
Right, because it's a vector field, and through this vector field, we're having this simple closed curve. And if we had a conservative vector field and started and ended in the same spot, we'd do 0 work. And what Green's theorem says is find the amount of work that's done on a simple closed, this is a big word. Can you please make a note? We talked about it earlier, but I didn't make you write it down. We talked about how the curve for Green's theorem, it's on a plane. It's a planar curve. It is on a plane. When we get into the next few sections, like Stokes' theorem, 15.9, it does not have to be on a plane. That's the main difference between them. Okay, so this is a planar curve for Green's theorem to work. It says if you're taking this simple closed curve through a vector field, and it's a conservative vector field, you'd get work done as 0. Start at the same spot, do some work, end at the same spot, you're doing nothing on a conservative vector field. That's why this would look really familiar. If you have a conservative vector field, this is literally how you would check it. You check these 2 pieces and see if they're equal. If they're equal and you subtract them, you'd get 0. And Green's theorem kind of intuitively checks for conservative vector fields. You don't really have to even know if it's conservative because it does it automatically. Does that make sense? And if you get 0, you go, oh, hey, simple closed curve, conservative vector field, done, 0. That's pretty easy. If it's non-conservative, this is relevant. And this is what Green's theorem says to us. If we have a non-conservative vector field and a simple closed curve, planar curve going through it, this would represent a line integral, or the work done, through a vector field along a simple closed curve. That's what that gives us. That means Green's theorem gives us the same thing. That means that if we can determine we have a simple closed curve and we have a vector field, we can always set up Green's theorem really nicely. So when we're finding this, we're going to do this line integral over a simple closed curve where it looks a little weird, so we're going to talk about that. But I want you to first understand that Green's theorem works simple closed curve, so Green's theorem is going to work here because we have one loop of a simple closed curve. I don't know if you're okay with that one. Let's try right now to set up Green's theorem, see how it works. The first thing I told you is you need to be able to identify P and Q. Basically, just look for the pieces of your vector field. Which one of these pieces is P? This one, because it's always joined with dx. Please keep this in mind. I mentioned this last time. A lot of times these can be switched around. So I told you to label them just so you don't start taking partial derivatives of the wrong thing accidentally. So I'm looking for the dx, and the piece right in front of that is P. I'm looking for the dy, the piece right in front of that is Q. I know you guys are okay with that because we practiced that a lot last time. I don't know if you are okay with that one. Now, because we have a line integral over a simple closed curve, it's representing work, Green's theorem is going to apply. Can you please try to set up Green's theorem for me? As you're doing it, what Green's theorem says is that it's really neat. The work done along that simple closed curve through a non-conservative vector field is equal to basically just the area that curve contains. That's what it's saying. That's really neat. So if we have a simple closed curve, it has this region, right? It equals an integral over the area of that region. That's interesting. So we're going to do this. We're going to set this up. We always do this first. We don't skip that step. Always set the double integral over the region, draw the region, and then finish your double integral. But set it up this way first. And then we do Green's theorem. So Green's theorem says take the partial derivative of Q with respect to x. So that's why we label it. We go right here. We go, okay, well, hey, what's the partial derivative of this thing with respect to x? Do you know it? 1. Okay, good. We got the 1.
1 equal 1 plus x. Or 1 plus x squared.
Honestly, I heard it was x squared. But I'm imagining that what you said was partial derivative of this thing with respect to x is 1. This is 1 over 1 plus x squared. That's what those derivatives are with respect to x. I don't know if you're okay with that one. And they said, okay, well, subtract the partial derivative of p with respect to y. Well, this stuff would be like y over 7. It's a constant. So what's the partial derivative of this with respect to y, please?
1 over plus x squared.
Before we go any further, I want to ask you one question. If I told you, hey, I want you to give me what the vector field is straight from this thing, could you do it? It's not a hard question. The vector field is always just pi plus qj. So if you wanted to find the vector field just off to the side here, the vector field that's giving us this line integral would be p I plus q j. And I'm trying to get you to see that because I don't want you to forget, I don't want you to lose what this means. What we're doing here, when we're doing this stuff, is we're finding the work done through a vector field. If you don't know what the vector field is, it really doesn't matter. Well, it does matter, I mean, you can do the problem, but I want you to put it all together. So we're doing work through a particular vector field. Which one? This one. That's the vector field we're doing work through along that particular curve. So hands feel right with that one. So when we get done with this, we have found work through that vector field along whatever the heck that thing looks like, and we'll talk about that in a minute. The first step is, see if your line integral fits Green's theorem. If it's a simple closed curve, it does. Set up Green's theorem. That doesn't mean you jump right to the region, because that can be kind of difficult. What that means is you take your partial derivatives, you write your region, you let it hang out for a second, and you write your dA, you let that hang out for a second, and you simplify as much as you can. Now, I know that when you wrote that down, you saw some things to simplify, right? So, we also talked about one more thing. This is a good problem, right? It's a really good recap problem. Because then it says, oh my goodness, we work this down, that we have a double integral over some region bound by that curve of 1. dA. What's that? Come on, everybody in class right now.
Area.
That's area. So what this is going to give us, this is going to give us literally the area of whatever that curve is. Does that make sense? Now, wait a second. Before we did this, if you remember the last two examples last time, we had some nice circles, and we had some formulas for areas of a circle, and we invented the formula for an ellipse. So we had a formula for that. Do you know what the formula is for this? I don't even know what that looks like. You could have done the problem. But let's say I didn't know if it was what it looked like. I didn't have a formula for it. That's when we go, okay, well, Green's theorem gave us this formula for area. Let's see what this region is. And that might take a little bit of work for you. So this region, what that looks like, and I'm not going to go through the whole process because we actually do this problem. It's called a lemniscate. Happens in Calc 2. When you first learn about graphing polar functions, you might have seen this. R squared equals cosine 2 theta. What it looks like is just figure 8. It just looks like this figure 8. You had one of those problems in some of your homework, by the way. And how could you do it? Well, you could take the square root, just plug in thetas and see what it gives you. But what happens here is we have this loop that starts here, does this, and comes back. And it's traveled in this direction. That's what the whole thing looks like. Now, what I want is the right loop. Explain to me right now why I want the right loop and not the whole thing. Keep in mind we're working with Green's theorem. Why do I want just one loop of this? Why does it someone else? Why doesn't it work with the whole thing?
Because you have to have a second double integral.
You would. Why?
Because it's two enclosed
Not
regions.
because, okay, that's it. Because it's not a simple closed curve. This would be a closed curve, but it's not simple because it crosses itself. Does that make sense? And it's on a plane, so it literally crosses itself. So on a plane, that's fantastic. Green's theorem works with planar curves. I can't do this guy, so I'm just going to eliminate that and work on just the right loop. So what we're finding here, what this does, this finds, so just keep our heads wrapped around this. This finds the work done by moving a particle one loop around this. This is what this is going to do. It's going to find the work done there. Does that make sense? It's also going to find, through that vector field, it's also going to find the area of that loop. Numerically, the work done along this loop through that particular vector field is going to be exactly equal to the area that loop contains. Show of hands if you understand the concept there. I don't want to overtalk it, but I want to make sure that you're here. We've had a weekend between, so I want to make sure that you guys are with me. Are you guys with me on this stuff? Okay, cool. So, how in the world are we going to do it? Well, I don't have a formula for the right area of the right loop of a lemniscate, but I do know how to set up a double integral. So let's think about this. Since this is defined in r's and thetas, and not x and y, and for heaven's sakes, I don't want to do x's and y's here, what type of double integral would you want to do? What do you think? One in xy coordinates or one in polar coordinates? So let's start defining the region. Our region, if I look at this, if this is the area, I'm going to erase this so we don't even think about it because you don't need it. Let's think back to our double integral days. If I start at the origin, am I immediately hitting the area of my region right from the origin? This is the region, yes? Yes.
Yeah.
So my double integral goes from, come on, you know it, starts from where?
Zero.
And then no matter where I go, I'm going to be hitting this curve. Well, we got to define that curve because we want r equal. So we look back at our function. Can you solve that for r? Sure, pretty easy. R equals what?
Squared.
So as far as our region's concerned, when I set up my double integral and I don't have a formula for a nice shape like a circle or an ellipse or something like that, then I have to go back to the actual polar function. I have to look at that, I have to graph it, and I have to set up my region. My region starts from 0 along the r to where it hits square root of cosine 2 theta. First question, are you guys okay with that one? So our r is just going through a region, that's it, going from 0 to the function itself. Now, the theta, that can be hard. You see, the problem with this curve, it starts at 0, it goes this way, then it comes back down and does this before it hits this section. So if I want to go from here to here, I can't start calling it things like, well, when you graph this, you get 0, you get pi over 4 that gives me this, you get pi over 2 and you get pi. Pi gives you one full rotation of this. But I can't do things like go from a larger value of pi to a smaller value of pi. Notice that the larger value of pi would be giving us this stuff when I plug in like 3 pi over 2 to pi itself. 3 pi over 4 to pi, that's where I'd be getting this section of it. So instead of thinking about like pi over 4 to 3 pi over 4, I'd be thinking of maybe negative pi over 4 to positive pi over 4. So when I'm setting my polar, I have to use angles. I gotta say where the stuff starts and stops. But if I don't want to go around the whole thing, I can't just go from like 0 to pi or 0 to 2 pi if you have one of those functions that creates a full circuit in 2 pi. I'd have to think about what's going to create for me this segment. And what creates for me this segment is this negative pi over 4 to pi over 4. Show of hands if you feel all right with that. So that's an important idea. So when we finish this setup, we get theta equals negative pi over 4 to pi over 4. Now there's only one more thing. It's going to be a really easy thing. Do we need to change the 1? Do we need to change the dA?
Yes.
Think back to polar, what's it become? Beautiful. Would you know how to solve it from there?
Yes.
What would you integrate first?
R.
So you get this 1/2 r,
Square.
and then you're plugging in a square root. Pretty darn convenient, yeah? Then you do a very simple integral on cosine 2 theta. You get it's just like 1/2 sine 2 theta. Plug it in negative pi over 4 to pi over 4, and you should get 1/2 out of that. Now, before we go any further, you tell me what that means. What's that mean?
Work done in
Tell me two things that it means. The first thing, what's it mean? That means area. We just found the area of this shape, the right loop of a lemniscate. We just found that. And now if you're okay with that one. Tell me the second thing it means. Consider Green's theorem.
Work.
That's work.
Done.
Done around this loop in the counterclockwise direction. But not just the work done around the loop, that doesn't make sense. The work done around the loop in this vector field. Does that make sense? You're getting it. You're getting it. It should be making sense at this point to you. Kind of cool, right? So if we're finding work, then we're going to put this like in a, put yourself in a test situation. I say, look, I want you to find the work done through that vector field along this thing. Let's think through what you could do with this. So firstly, if we're finding work done along a curve, we got what? What type of a situation do we have? Find work done through a vector field along a line. It's called a line. What gives us work through a vector field along a line? A line integral. We got a line integral. We're just setting up a line integral. We've talked about several ways to do that. We've talked about just basic line integrals when you don't have conservative vector fields, where you just added up all the segments. You remember talking about that? Then we talked about line integrals on conservative vector fields. Now we're talking about line integrals on non-conservative vector fields, but where we have a simple closed curve on a plane. That's where we're at right now. So let's start thinking that way. We got a vector field, we're looking for work done, and we have a series of segments that come together to form a triangle. Does that make sense? We have a line integral. There's three ways to do it. Number one thought you might have is, well, check for conservative. You could do that. Is it conservative? No. But you could check it very easily. Partial derivative of this with respect to x, partial derivative of this with respect to y, they're not equal. Does that make sense to you? You go, okay, well, if they're not, so our integrals, line integrals, and conservative vector fields, that fails. We can't do that stuff. We could do, now listen, we're not going to do it this way, but we could do this. We could graph this region Now we could do this. We could separate these three segments into 1 and 2 and 3. And we could parameterize them in terms of a vector function. And we could literally do a very simple line integral for this and this and this using that vector field and add up the results. You remember that? We've actually done it with segments. But we only had 2 segments at a time. Why? Because as soon as you have 3 segments that close a loop, what could you do instead of adding up 3 different line integrals? What could you do? Let's try this again. For a lot of you, it just went right over your head. Listen, the first thing you might try for any work done through a vector field along a curve, that's a line integral, folks. That's what that means. So you go, okay, line integral, absolutely. How many different ways do we have to do line integrals? 3. We're going to have 4 by the end of this next section. So 3 different ways. One of those ways is just universal. Through non-conservative vector fields, you just take each segment, go, hey, that's one line integral of this one segment through that vector field. You parameterize it, you do it. Hey, that's another segment through that vector field. Parameterize it, do it. Hey, there's another one through that vector, parameterize and do it, and then add up the result. That's one way you literally could do this. In fact, from before, if I don't have one of these legs, that's what you would have to do. Does that make sense to you? You'd have to do that because it's non-conservative vector field. It doesn't make a loop. Then we go, okay, if it's non-conservative, I can't use the conservative stuff. But if it's non-conservative and it creates a loop, then I don't have to add up all 3 line integrals. I now have what? Line integrals through non-conservative vector fields that create a simple closed curve. And you go, triangle's not a curve, man. Yes, it is. It's just a silly looking curve. It is closed. It's simple. It doesn't cross itself. That's a simple closed curve. And if we traverse that in a positive counterclockwise direction, what Green's theorem will give us is the work done along that simple closed curve that contains this region by looking at the double integral over that region of this thing from your vector field. That's the whole idea. Is it making sense to you? I don't want to bore you to death, but I want you to see the connection about how the last 3 sections, you're finding the same thing. It's just you have different scenarios. Number 1, universal, non-conservative, add them up. Just do an integral, line integral for every single different segment. It just sucks. It's hard. Then you go, okay, what about conservative? We have a very special case for conservative. It's pretty cool. It's pretty easy. You just do your antiderivatives. Done. Plug numbers in. Now, and it's independence of path. You recall that. Now it's, hey, let's suppose you're back to non-conservative, but you got a simple closed curve. Man, Green's theorem. So right now, I need you to verify for me, if this was on a test or something, you would recognize Green's theorem right here. Show of hands if you do. It's work done. Is it a simple closed curve? And do you get a vector field? Green's theorem. Done. Set up Green's theorem right now for me, would you? I want you to label P, I want you to label Q, and I want you to set up Green's theorem. Do not skip down to this step. Show me this step and simplify if you can. I want to see that. That right there is just basic work done through a vector field along a curve. That's what a line integral is. Does that make sense to you? And then we go, well, now let's look at our curve. If our curve does this, which is what it does, now Green's theorem applies. You guys see the difference? Look, you ready? Ready? Green's theorem? No. 2 sections ago. Non-conservative vector fields add up the segments. Green's theorem? Yes, simple closed curve. And since we have one, that's our setup. Now, I do want to show you, I wouldn't do it this way, I'd do the shortcut, but I'm going to show you the like where this all comes from, and then I'll show you the shortcut. Does that make sense? Maybe I'll show you the shortcut first. Can you identify what P is from your vector field? That means that's Q, yeah? So, hey, look, if this always gives you work done over simple, just work done in general, and you know your P, and you know your Q, you can jump right to that. So even though this looks a little different from what we're doing, we will be getting this from this thing. And all you gotta do is write P dx plus Q dy, and that's going to be exactly the same thing. Show of hands if you're all right with that one. Do you see where it comes from? That's what, I mean, when we got the vector field from this thing, we should be able to get this thing from the vector field. So if you have P and Q, you can literally go back and forth between a vector field and the work done over that vector, through that vector field along that planar curve. Head down if you're okay with that one. Now if you want to see the math behind it, here's the math behind it. The math behind it says, well, what is f dot dr? Well, f dot dr is f dot dr is simply this dotted with this. Hey, that's f, that's dr. Do you see how when you do a dot product, you get this here plus this here? It's the same thing. You have to get the same thing. It's just we can shortcut it, because if you don't want to do a dot product, you go, hey, put P with dx, put Q with dr, you have a line integral right then and there. You still okay with that one? You having fun yet?
Yes.
Interesting? Is it starting to, am I starting to wrap this up for you? Because the next section is going, we're doing 4 at once, but the next 4 sections are going to put everything together for this whole chapter. And I need to make sure you're good at this stuff before we get there. Do you feel competent with Green's theorem right now? I see a lot of head nods, but I don't see a lot of, I don't hear a lot of words. Do you know when Green's theorem works?
Yes.
Over vector fields along what?
Simple closed region.
Simple closed planar curves. That's what I need you to know. If you have one, Green's theorem. So, did you make that far at least? Now, because we got a line integral over a simple closed curve, let's go ahead, let's set up Green's theorem. If you haven't done that, I want you to do Green's theorem right now. Did you? I don't want you to do anything with the region. Not right at the start. I just want you to leave it there and then consider your region, okay? We would have, hey, the same P, the same Q. It literally has to be the same. Just take the partial derivative of Q with respect to x. Subtract the partial derivative of P with respect to y. dA. Head down if you're okay with that one. Now, that's what Green's theorem says. It says, hey, the work done along this, through that vector field, along this simple closed curve, is equal to the double integral of whatever you get out of this, whatever this thing is, over the region that curve encompasses, encloses. That's what it says. All we have to do is define the region. In this case, since we're going from 1 to 1, or 0, 1 to 1, 0, this line, this line right here could be defined in a couple different ways, and it really doesn't matter. It's a pretty basic region. Me personally, I like going dy first. I define this as 1 minus x, y equals 1 minus x. Head down if you're okay with that one. So if I define this as y equals, would I be going dy first, or would I be going dx first? Set it up. I want you to set it up. Tell me quickly, what's y going from and going to, please?
0 to 1 minus x.
Beautiful. Since I'm going dy from y equals to y equals, it's y simple, I need dy. And then x goes from
0 to 1.
Beautiful. dx. Could you have switched it around? Absolutely. Doesn't even matter. If you want to solve that for x, that way you avoid integrating with respect to y, you can do that as well. Does it matter? Not really. Maybe for some distribution, you might have done that one. Me personally, I didn't. Would you know what to do after this? What would you do?
Like right in perspective line.
Yeah, I might have actually, if I had thought about this a little bit more, I might have done dx first, just so that I avoid dealing with that y first step. But either way, any way you want to go, this needs to give you 2/3. Quick question before we end this. Is this the area of that triangle?
No.
Why not?
If the integral isn't perspective line.
If it's not 1. If this had been 1, that would give us the area. Obviously, that triangle would have an area of 2/3. All right, but base times height divided by 2 is not going to give you 2/3. It's going to give you 1/2. So it's not giving us the area here. What it's giving us in this context is the work done along that simple closed curve through that vector field. That is exactly what I want you to know, and that's how Green's theorem works. Have I explained this well enough for you guys to understand it? Okay.